looks like Ron's gonna get us going here. I need to loosen that up.
Hiya, stargazers.
Hi, Ron.
I'm Vice President, and I guess we got a lot to talk about before we introduce our esteemed guest from JPL. So I'm going to just take over and do it. John Callas, did we find somebody to run the microphone for the Q&A later?
Yes.
Okay. Then let me start the program by my newly, recently, last minute, authorized, what's the word I'm looking for? And the power vested in me, the meeting is now underway at the Santa Barbara Astronomical Unit. Good show, Chrissy. Is she here? Chrissy, is I was going to introduce her. Oh, there she is in the back. Let's get Chrissy a hand. Lovely as heck. So much fun to watch your program. We're going to do the business part of the meeting. Jerry, our president, our beloved man in charge usually, came down with a medical problem. It had nothing to do with the variants running around or RSV. I'm sure he's got his shots, like I just got mine too, the flu shot and RSV. And that COVID is still out there, that's why. These things also make a good covering for that waddle, that rooster craw, the old Nobody knows that one. Jerry is watching somehow. I hope I didn't cover up something here. Somehow we're putting this on Zoom, right? YouTube. On YouTube? I don't think we're on YouTube.
We're doing it on Zoom and it gets uploaded to YouTube later.
Put that down. I just broke the cup that I get from the speaker afterwards. Chuck McPartland and his wife Pat McPartland are our outreach coordinator and merchandise manager. They are in Ireland and probably watching us, or part of Zoom. Maybe it's 1:30, I think they're in. Maybe 2:30? Anybody know Irish time right now?
It's 8 hours. 8 hours ahead.
It's nothing to him. He's a telescope guy, so that's the sort of hour he keeps anyway. And Colin Taylor's not here. He's our treasurer. Call him Captain Wide Brim Hat. Am I covering?
Hit the slides here. Everything changed. Like we want to say thanks to Chrissy for doing the planetary show, and then starting programs here, and then here's our website that you can provide information about us.
Okay, I'll be right
And then
reading on
we did Pat does that, and then the next two will be Chuck.
You want to do it, Tom?
Yeah.
This is our former president, our last president. He was a good guy. He's now our webmaster, and I think he deserves applause. All right, we got lots to talk about, so let me get to it, because this gentleman from JPL is raring to go and brought his family up, and I'd like him to introduce them, maybe if you can, or at least we'll say hi when we have him stand. So if I just keep pushing the button, you can buy things. I have most of this. At least I have the jackets. I have 2 of those. They get me through the winter. Best thing I have. I also have a mug. And so will John Callas before the end of the evening. Plus, I think, yes, the bag. Got goodies here for him. Chrissy's here. Only person here from the club that's on the board is Tom. You just met him. Colin is not here. Tessa Flanagan is here. She's going to be our secretary. Wave at us. Raise your hand, Tessa. There she is in the back. So glad you're in recession and everything's getting better. Look healthy. We'll have a meeting online next Saturday prior to, hopefully without this kind of weather, our star party that's on the 2nd Saturday of the month. And let me give us some other guys who may be watching this. Tim Crawford and some of the others, including the president, Jerry Wilson, have a program that's been on YouTube for years. I guess it's on YouTube. It's a Zoom thing on Tuesday nights called The Workshop. You can build your own telescope. They talk about grinding and polishing, concave and convex mirrors and lenses and all of that. Tom Whittemore is not here, but he is the editor of our incredible monthly newsletter. It goes out to everybody online. And he also takes part in a Monday morning 1-hour podcast. A blog we put out is going into our 3rd year soon. We'll have our 133rd episode this coming Monday morning, 11 till noon. You can watch on YouTube, called the SBAU Astro Hour. And it's, I think, one of the best programs for astronomy. It's like taking a course out at the university and not having to pay for it, 1 hour at a time. I hope to get a degree just from running the damn thing as vice president. We're a pretty good club. Just out of curiosity, raise your hand if you're new. Never come before. We want to... we're going to get the details from these people. Now raise your hand if you're a member. Okay. Well, good deal. Thank you very much. It's a good club. I'm proud. What the heck am I doing vice president? I feel like Kamala Harris and Mike Pence all wrapped up in one person here. Nevertheless, let me run down different things that are happening. Press the button. Did we go by stuff I should have talked about, Tom?
Well, you kind of covered it, so try to hit the right arrow there and see what happens here.
Click the mouse and then the right arrow.
The right arrow, okay.
You said what?
Click the mouse and then the right arrow.
So you can click the mouse and then.
Okay, there's the.
You want me to read all this to you?
No, you could summarize that and then hit the arrow again.
Actually, Tessa gave me something. You want to come up and tell us, Tessa, everything that's happening, or can you yell it out from back there?
I didn't memorize it.
Here, do the stairs on the left.
It went out on certain emails today, and this is kind of important stuff.
Didn't coordinate this.
Tessa is ready to take over secretarial duties, which right now are being run by Mr. and Mrs. McPartland, even though he's our outreach guy. I just had it, and I'm trying to figure out what it went. Is it? Yeah. Okay. Might be down there in my seat.
Okay, here's your seat.
Is it down there?
Oh.
Oh, there we go. Okay. So, general, I don't need that. General meetings must end at 10.
Please use the microphone, please.
Okay. The general meeting needs to end by 10 o'clock, and then we need to clear out of this room as quickly as we can so that the museum staff can clean it up and get the chairs all put away. They're not requiring us to do that, so let's thank them and move out quickly. And then make sure you put your car out before 11 o'clock, because at that point, they need to lock up the parking lot according to the conditional use permit that the neighbors have allowed us even to use the place after dark. So let's honor that. All right, so the October 6th, so the next general meeting will be held in Farron Hall, right next door to the where the planetarium is. It won't be in here. So if you come here and go, oh, wait a minute, where'd it go? Just aim for the planetarium. And then the partial solar eclipse viewing on Saturday, October 14th, will be held at the Camino Real Marketplace. So people who are bringing solar telescopes, setup is at 7 a.m. And will end by noon. It's going to be in the sunken area in front of Starbucks, around where the movie theater is. So the actual partial solar eclipse for Santa Barbara begins at 8:07 a.m. Maximum is at 9:22 a.m. and it ends at 10:47 a.m. And for folks in outreach or officers, this is a second Saturday. So in addition to the solar eclipse early in the morning, we have the planning meeting at 5 on Zoom and a regular star party at the museum starting at 7:30. And then we're coming up on the annual SBAU campout and potluck up at Lake Kachuma. So the potluck is on Saturday, October 21st at 5 p.m. And Pat McPartland will be back for that for the September meeting, and she's going to have us sign up for both the potluck and camping in general. So let's see. No, she's not going to be at the September meeting. That's now. She will be at the one in October. So if you want to go to either the potluck on 10/21 at 5 o'clock, and either be here to sign up or make sure you send an email to somebody, to one of the officers. And then if you want to camp out, then the camp out starts on Friday, October 20th at 1 p.m. and ends on Sunday, October 22nd at noon. And we're out at Mohawk Shores, which the Kachuma Campground kindly lets us use because we do star parties all summer. So we have a very nice partnership with them. And it's a wonderful place, and you've got a telescope, you have a chance to go and goof around all night, and people will come and look at things, but we're not specifically aimed for public star parties. So thank you.
Thank you. I want to introduce another member of our club that we couldn't do it without. He's part of our crew that of talking heads on the screen on Monday mornings, ready for show number 133, SBAU Astro Hour. Bruce Murdoch, are you here? Just raise your hand. With his lovely wife Bonnie. And Bruce is also president of the Santa Barbara Theater Organ Society. You want to tell us what you guys are doing with the Big Arlington?
Well, we're
Big Arlington organ?
Pardon?
The big organ, right?
Right.
The Arlington.
Repeat yourself?
There's a big organ.
Right, it's a four-manual 27-rank theater pipe organ.
Right.
Installed in the Arlington. Most people don't know it's there. It lives below the stage. It's on a big lift. It comes up through the stage. On the second Saturday of the month, we hold an open console. Anybody can come down, ask questions, take pictures, play the organ. We'll show you up into the chambers where all the sound is created, and it's a lot of fun. From 9 until 11. Typically, the second Saturday, we don't get a notice, we don't get okay for the theater until the week before. Because if they got somebody that's coming in who's going to pay them money, we have to move a week one way or the other.
So Bruce has got a thin line of incredible stuff he has to do daily, but he has more fun with us, I gotta tell you. And you were out in the middle of the night with your instrument, aren't you? You go up on peaks, you know, Cielo, and
Well, I don't know about Cielo for the eclipse, but
right.
the best place to go is Kachuma for viewing.
Really?
Oh, yeah.
Yeah.
All those campfires, huh? They did appear, right?
Well,
I plan to.
because of the mountains between us and the light sources, all the light pollution.
Helps to have camping equipment to go to that big camp out. Here's what's coming up, because I want to bring my speaker on, ladies and gentlemen. Next month, October 6th, as Tessa told us, we're going to be down in the back. Looks like the group we have in here might just fit in there, because there's slightly less seats than in here. And our speaker will be a world-renowned star columnist for astronomy magazine, Sky Bob Berman. He calls himself Sky Bob. Somehow we got him. It'll be in Farron Hall. Hopefully the sound will be good. He's the first talking head we'll have for a Zoom speech in a long time. We've been very lucky getting people that will come up here and love Santa Barbara and grace us with their presence. Following month, Friday, November 3rd, Dr. Matthew Povich from Cal Poly Pomona Foundation. He's an outreach scientist for IPAC, IPAC. You look that up. December 1st, we got two things to do. I want to just put the word out early. We're going to have a club election. So I may be replaced. Jerry, all of us may be replaced. We might elect Tessa in as permanent secretary if she's running. You may want to run. You may want to be on a committee. By all means, let me know. Check out SBAU.org for the details. That's one thing. That night we'll have, I guess, a show of hands and try to get it from the people watching at home on Zoom or on YouTube. And on December 1st, our in-house homegrown version science presentation where we invite members of the club to speak. We're going to feature three people who I believe, two of whom are in the room with us. Mike Hardwick is going to show some incredible pictures he's taken with one of his 5 telescopes. Mike is one of the best historians in town and a definite freak for astronomy. And Earthquake Dave Feinberg is also here. Raise your hand on Earthquake. Working it out with Tom on your thing about meteorites, right? Okay, that happens to be the specialty of our outreach coordinator, Chuck McPartland, but he gets to sit back and see another version that night. And then a gentleman who is a member, makes it over from Ojai when he can, Rex Meach, is going to talk about navigation using stars. And that'll be 20 minutes each for an hour in December. So there you got it. Let's now meet the man from JPL. Because he's a very nice gentleman. And he said he had smooth sailing getting up here. Let him tell you about that. Ladies and gentlemen, he is a physicist at NASA's JPL, Jet Propulsion Laboratory, where we might be able to take a group, I've now learned, someday. That would be fabulous. We've been kicking around. Where are we going to go on our big summertime field trip? Pasadena has a BA in engineering from Tufts University and his master's degree and PhD in physics from Brown University. He was project manager of NASA's Mars Exploration Rover project. In fact, I think it says something like that on his shirt, which you can buy from JPL. Both Spirit and Opportunity were operating rovers that are based down there on the Red Planet for over a decade. And then the man led the joint NASA-NSF exoplanet observational research program. And now he is manager of NASA's fundamental physics program as well as teaching math at Pasadena City College as an adjunct assistant professor. Let's have a big hand of applause for ladies and gentlemen, John Callas. On this thing, but if you'd like to hold it.
Well, good evening. It's wonderful to be here. Very excited to be here for the Santa Barbara Astronomical Unit. You know, when I use the term astronomical unit, I know it's a very large distance, 150 million kilometers. So a Santa Barbara Astronomical Unit must be something even greater than that. So what I want to present to you tonight are the great scientific questions of our time. Are we alone? And then I preface it, in the dark. I'll start with this image. This is a recent image by the James Webb Space Telescope, a spectacularly performing instrument in space. This is the Deep Field Survey, and what you see are just a few stars, but a myriad of galaxies. And you can see the two great theories of contemporary physics, general relativity and quantum mechanics, at play in this image, because the luminous stars are clearly a result of the forces that we can understand in the laboratory, things that can be described by quantum mechanics. And then you also see the structure in this image is governed by gravity. Now, specifically, if you look at the arc galaxies around it, you're observing gravitational lensing. So a massive object is acting like a giant lens and distorting the light from those galaxies as we observe them here on Earth. But as magnificent as this image is, it brings up several disturbing questions. But first, let's do some math. In this image, there's about 10,000 galaxies observed. And this field of view corresponds to about 1/10,000,000th of the nighttime sky. So if this is representative of the number of galaxies you would see per unit of sky, then you would take 10,000 galaxies and multiply it by 10 million, and you get a number like 100 billion. And so this says our observable universe may have something of the order of 100 billion galaxies. And most of these galaxies are actually rather garden variety. This is M81. It's a galaxy very much like our own Milky Way galaxy. And this is a galaxy of roughly 100 billion stars. So, okay, let's do a little bit more arithmetic here. If we have 100 billion galaxies that are averaging like 100 billion stars, we get a number like 10 to the 22. That's a number with 22 zeros behind it. as the number of stars in our observable universe. Okay, wow, well that's a really large number. To give you an idea of how big that number is this weekend if you go down to the beach and you scoop up a shovelful or a handful of sand and you pour out the sand and you think of how many grains of sand are in your palm, and then look out along the beach and wonder how many grains of sand are on that beach. And then think about all the beaches along all the shorelines of the entirety of the earth, and while you're at it, throw in all the sand and all the deserts all over the earth, and you start to get a number that may approach 10 to the 22. So in other words, there are more stars in our universe than there are grains of sand all over the earth. And so this is just an unfathomable number of objects out there. Okay, how many of those stars have planetary systems or Earths around them? Well, let's try to answer that question. As you heard earlier tonight when observing a solar eclipse, always use protective eye gear because the sun is so bright. Well, if we try to look at these stars to see if they might have planets around them, we have the same problem. The star is just too bright. In this particular image here, this is actually a dwarf star down here. So this is something that's really large and really far away, and that was about the best we could do about trying to see compact objects around a star. Well, we've since done a little better. This is the Gemini Observatory, it's a Gemini telescope, in which we use a coronagraph, which is a device that blocks the starlight so you can see what's around it. And we see in this particular image 3 giant planets in orbit around the star. Now you have a sense of scale down here. So this is 20 astronomical units, and not as large as a Santa Barbara astronomical unit. But you can see that these objects are much, much larger than our own solar system. And so how could we see an object where you might have a planet that's only within 1 astronomical unit? It's quite difficult. So we have techniques to do this indirectly. What is called the transiting technique. And this is where we don't directly detect the planet, but we infer its presence by the shadow or the light that it blocks as it passes in front of the star. And this is a very powerful technique because if you look at that star and measure the amount of light that's coming out of the star, you'll see that you get a dip for a period of time and then it restores to the nominal level of the star. And then it repeats with each orbit. So not only do you determine the presence of an orbiting object, but you get the orbital period. And depending on how much it dips down, you get the size of the object because this dip is just a ratio of the size of the planet passing in front of the disk of the star. So you can get the diameter or the radius of that planet with its orbit, and you suddenly know quite a bit about what's going on. I'll give you an example. This is from 2012. This is the planet Venus passing in front of the disk of the sun. This is a picture I took from the roof of Pasadena City College at the time. And so this is a powerful technique. And we've been using this to detect planets. There's another technique we can use, and it's called the radial velocity technique. Now this is something we've all done as kids, where you have a rock on the end of a string and you spin it around your head. And the heavier the rock, the more your body has to compensate for it. For every action, there's an equal and opposite reaction. Well, it turns out stars wobble because planets might be orbiting. So our sun wobbles as the planets go around it. Now, it's a small effect. It's a tiny effect, in fact. And of course, it has a very slow period. The Jupiter dominates in our solar system, so you have to wait 10 years to see the effect of Jupiter. Our Earth, of course, takes 1 year. Now, the way we determine that effect is by looking at the star, because you don't actually see the star wobble. But if you look at the spectral lines in the light coming from the corona of the star, you'll see those lines move back and forth due to the Doppler shift, because the star is wobbling. And so with this technique, we can also detect planets. We can get their orbital period, but in this case, we can get the mass of the planet, because the more massive the planet that's orbiting, the more the star responds, the larger the Doppler shift, and the bigger the back and forth the spectral lines go. So with these two techniques, we now have a very powerful set of tools to detect planets around stars. And here is a plot where we have both measurements, and we've got planetary mass along here, and planetary radius here, and we've plotted on here curves that correspond to compositions of different materials. If we had a planet that was completely a solid piece of iron, it would lie along this line. Here is 50% iron, manganese, silicates. Here are just basic silicates. Over here would be water worlds. And down here, here's the Earth, and here's Venus. And you can see right away, without directly detecting these planets, which are corresponding to these error bars, we suddenly know a lot about them. We know their size, we know their mass, we know their orbital period, so we know they're distant from the host star, and now we have an idea of their bulk composition. So without direct detection, via these indirect techniques, we know a lot about exoplanets out there. Okay, so how many exoplanets are there out there? Well, we had a mission called Kepler, which job was just to stare at a particular part of the sky for an extended period of time. And this shows the field of view, this checkerboard. This is an array of CCDs covering a huge amount of sky, about the size of the moon. So we're staring at about 150,000 stars for about 3 years. You know, why 3 years? Well, if you want to detect like an Earth-like planet that has an orbital period of once a year, you want to see that transit at least 2 or 3 times to confirm that it in fact is a repeating cycle, that it's not just a one-off event, it's not just a Klingon cloaked spacecraft flying across the star one time. And so Kepler stared for 3 years at this one part of the sky, and here is some of the data that it detected. It found about 350 Earth-sized planets, about 800 super-Earths, about 1,300 Neptune-sized, about 200 Jupiters, and 81 larger than that. So in here there's about 2,700 exoplanets that it found looking at 150,000 stars. So wow, is that representative of the number of exoplanets we find if we started to look at all of those 10 to the 22 stars? Well, I haven't told you the whole story. The transit technique only works if the planet transits in front of the star as we view it here from the Earth. What if it's going around like this and never transits this way? Well, it turns out only about 0.5% of planetary orbits will transit such that we detect them. So we're missing 99.5% of the planets. So instead of 2,700, there should be about 200 times as many. Let's see, 2,700 times 200, do the math, that's what, 540,000 exoplanets for 150,000 stars. So that means, on average, those stars might have had between 3 and 4 planets, exoplanets, each. So we're not just talking about one planet, we're talking about planetary systems around pretty much every star. And does that extend throughout the universe? We don't see why not. So now we have 10 to the 22 stars, and each of those stars has 4, on average, exoplanets. That's an even bigger number. We don't have enough sand on the Earth to conceive of how many possible exoplanets are out there. That's an inconceivable number. That's really huge. I mean, it's bigger than the Santa Barbara Astronomical Universe. And so what do these planetary systems look like? Well, we can tell you something about them indirectly. So here's the Earth, our solar system, shown to scale to this one particularly called Kepler 62. And these are rocky, terrestrial-like planets orbiting the system. Now notice this solar system is smaller than our solar system. It's a dimmer star, but the green that you see here corresponds to what we call the habitable zone. When you build a campfire, if you sit too close, you're too hot. If you sit too far away, you're too cold. If you're just the right distance for that given size of campfire, you're nice and comfortable. Well, it works that way with planets. If you're too close to the sun, you're like Mercury. Even it's burning hot, there's no, water on the surface, or Venus, where the surface is so hot that it's, melts lead. Or you could be out at, beyond Mars or Jupiter where it's really cold, or you could be right where the Earth is, in the middle of the habitable zone, where liquid water exists. Liquid water is important because everywhere we find life, we find that it requires liquid water. So if we're searching for life out in the universe, which is one of the great questions we'd like to answer, finding planets that have liquid water on their surface would be a really exciting thing. And notice that here, in this one particular exoplanetary system, we have a couple of terrestrial planets that orbit in the habitable zone. So how common is this? Well, it turns out it's pretty common out there at all those exoplanets that we're just detecting. I mean, you saw that, remember that plot I showed you earlier, there are a bunch of terrestrial rocky planets that are like the Earth that are out there, and some of these are now orbiting in the habitable zone. So suddenly we have a large number of putative worlds out there that have liquid water on their surface. And of course, now you ask more questions. How many of them have atmospheres? How many of them have in conditions that are conducive to life? Because it's not just water. Obviously, there are many things that are necessary for life to exist. So let's look at our own solar system as a proxy for those exoplanetary systems. So here's Jupiter, and you can see the Galilean satellites. This is an image taken by Voyager. Let's zoom in on Europa, one of the Galilean satellites that's of great interest. Europa is an ice-covered world, but as Voyager flew by, and then subsequently the Galileo mission, they determined that underneath the icy surface of Europa is a great ocean. And that this ice is actually floating on top of that. And you can see it's fractured, very much like the ice sheets at Antarctica or the Arctic during the spring and the fall when those ice sheets begin to break up and start to float around. And this is significant because, wow, this is another place in our solar system that's outside of the habitable zone that has liquid water. Why does it have liquid water? Not because it's solar heating is making that water liquid, it's because the tidal forces of the giant planet Jupiter are wrenching that poor little moon Europa to keep that liquid ocean, liquid. So there is tidal energy that is driving the forces on Europa. And that energy can also be a mechanism to drive life, because one of the other essential ingredients for life, in addition to liquid water, is you have to have a source of energy. Here on Earth, most of that energy comes from the sun, but out of Jupiter, it could come from tidal energy. This is what's called the Lost City. It's located in the Atlantic Ocean here on the Earth. It's not at the mid-Atlantic ridge. It's actually far away from the mid-Atlantic ridge. And these are serpentine carbonate towers that are forming from not hot water, but warm water that is seeping up through the crust into the cold, briny ocean. And what's happening is the rich carbonates in that warm water precipitate out when they encounter the cold salt water, and they form these towers. But when astrobiologists study these serpentine towers, what they find is they are factories for the manufacture of methane and free hydrogen. They're taking inorganic carbon, like carbon dioxide, and water, and producing an electrochemical reaction to manufacture methane. So methane is the fundamental building block of organic molecules. We are made of organic molecules, and they all start with methane. And so now we have an example here on the Earth of a very simple physiochemical structure. I mean, the chemistry involved in this is so simple you can do it in your own kitchen. And so could this be happening on Europa, where we have just tidal energy taking some of those carbonate minerals, mixing them with a briny ocean of Europa, and it's believed that the ocean on Europa is briny, that it is salty, forming these serpentine towers that are producing organic compounds, and I also mentioned free hydrogen, such that we're producing the kind of electrochemistry that can drive metabolic systems, systems that are going on in our cells right now. Could this have been the birthplace of life here on Earth? Many scientists are conjecturing that right now. This kind of activity could be happening on Europa today in our solar system outside of the habitable zone. If we zoom over to Saturn, the great stately rings, and we encounter Titan. Titan is a moon that's almost the size of a planet. It's the largest moon, the largest satellite in our solar system. It is covered in a thick nitrogen and methane atmosphere, methane, organics. And when we look at the surface, this is a synthetic aperture radar image taken by the Cassini mission of the surface of Titan. You can see things that look like flow channels. And this looks like a shoreline to a lake. This is a complex organic compound lake. Methane, liquid methane, ethane, and other compounds are forming this. And so Titan alone has this, it comes already with a rich organic world. And so what kind of organic molecules are producing? So yet another place in our solar system. While we're still at Saturn, if we come to Enceladus, we see that Enceladus has geysers on its southern hemisphere. These are liquid water geysers. So Enceladus is an ice-covered world with also a liquid ocean inside, and that ocean is leaking out and it's jetting out. And again, we ask the question, what could be going on inside the ocean? What might we find in these jets coming out of Enceladus? Again, because Saturn is a large planet, it is exhibiting a large tidal force on Enceladus, keeping that water liquid, and also serving as a source of energy. And then we come to Mars. I spent most of my career on Mars. Mars is, of all the places outside of the Earth within our solar system, that's most likely to have supported life. This is a ground-based telescopic image of Mars. You can see its polar caps. It's tilted on its axis 25 degrees, very close to the Earth's 23 1/3 degrees. So Mars has 4 distinct seasons. And these dark features, we call them albedo features, would change with the seasonal cycles. Here's an image taken by one of the Viking orbiters from the mid-1970s as we approached Mars. And you can see that right away Mars has an atmosphere. It's a thin, tenuous atmosphere. It's 95% carbon dioxide. But it's only about 1% as thick as the Earth's atmosphere. And if you look at these craters, you can see they kind of look like the craters on the moon, but they're softened and eroded. There have been physical processes at work on Mars that have been reforming its surface. Very different from the moon, our moon, which has been, the surface has been pretty much unaltered for billions of years. So the Viking mission landed 2 fixed landers in 2 locations on the surface of Mars in the mid-1970s. They were meant to search for life. They had 3 experiments on board each lander. They had a robotic arm. They took soil samples. They put them into the 3 experiments. And they found no conclusive evidence for life. I say no conclusive evidence because there's still some results that are debated today, almost 50 years after the fact. But Viking went to Mars with our understanding of life as we knew it in the late 1960s, early 1970s. And since that time, our understanding of life here on Earth has greatly expanded. That we find life in the most extreme environments here on Earth, frozen in the ice, deep, kilometers underneath the ground, in incredible temperatures and pressures, in arid environments, in very acidic environments, and it thrives. And so, surface of Mars is not so bad compared to some of the conditions where we find life here on Earth. But Viking kind of threw a wet blanket on the exploration of Mars for almost 20 years, and it wasn't until 1997 that we went back to Mars, and that's with the Mars Pathfinder mission that landed the very adorable Sojourner rover on the surface. Sojourner is about the size of a microwave oven, and when it comes to rovers, size does matter. The bigger the rover, the bigger the wheels, the larger the obstacles you can go over, the further you can go. Sojourner can go much further from the lander than you see in this image, only about 10 meters or a little over 30 feet. And so it was kind of dog leash constrained to the lander. And we were excited about, well, what's over the other side of that ridge, or what's this dark rock here? So this was a technology demonstration mission. Could we get to Mars, and could we put a rover on the surface? At the same time that Sojourner was on the surface, we had another mission called Mars Global Surveyor that went into orbit around Mars. And as its name suggests, it was meant to do a global survey of the planet. And this is some of that data. This is altimetry data of Mars taken by Global Surveyor. So red and white are very high altitude. You can see the Tharsis volcanoes and Olympus Mons. And then blue and purple are very low elevation. You can see Hellas Basin here. But if you look over here, you can see these giant flow channels that look like they might have been giant rivers at the time. And notice that this northern hemisphere of Mars is not only very low, but it's very smooth. It's one of the smoothest surfaces in the solar system. The only surface in our solar system that's smoother than this is the bottom of the ocean here on the Earth. And so, did Mars have a great northern ocean at one time? And today, it has since lost that ocean. Those are some of the questions we have. This is an image taken by Global Surveyor looking at a canyon system. So this is about 3 kilometers, about 2 miles across this field of view here. So you see this canyon system here, and to the geologists, they can tell you that this was carved by water. They can do that by looking at the slope, by looking at the viscosity and density that was required to carve a channel like this. And so this was carved by liquid water. And because you have this narrow channel down the middle of it, this was carved by slowly flowing water. So this didn't happen overnight. This wasn't a catastrophic flood. This took thousands of years, millions of years to form. So we have a problem. Today on Mars, the atmospheric pressure is only about 1/100th of what it is on the Earth. It's about 6 to 8 millibars. If you remember your phase diagram for water from high school chemistry, okay, if you don't, I have it here. Remember this, pressure versus temperature. And here is where water is a vapor. Here is where it's an ice. And here is where it's liquid. And you have this thing called the triple point. And so here's standard atmospheric pressure. And you can see that water freezes at 0 degrees C and it boils at 100 degrees C. But below a certain pressure, it's no longer liquid. And once you get below, it's called the triple point. This is the atmospheric pressure on Mars today. So water can't exist as a liquid on the surface. Yet we see evidence that liquid water flowed for tens of thousands, maybe tens of millions, maybe billions of years on Mars. So Mars must have had a thicker atmosphere. And it must have been warmer than it is today because it was still, Mars is minus 100 degrees C. So even if you had higher pressure, all that water would have been in ice. So Mars must have had warmer temperatures and a thicker atmosphere than it does today. Well, what happened to Mars? Well, those are some of the questions we want to find out. And one of the best ways to do that is to go back to Mars, but this time with a much more capable rover. This is my rover, the Mars Exploration Rovers. And you can see it's a larger vehicle. You can see the people standing around it. These are normal-sized people. So you can see this is about the size of a riding lawn tractor. It's 6-wheel drive, solar-powered, radio controlled, so it takes everything with it. So it's not going to be limited the way Sojourner was. It has a mast that supports a set of cameras. You can notice the cameras are up here that are pretty much at human height. These cameras can pitch around and look up and down, so very much like your own head and neck operate on Mars, so it will give us very much a human perspective. The cameras are ranged as stereo pairs, so the rover has depth perception, just the way you and I have depth perception. So when we take images, they're inherently three-dimensional, and this is a really powerful tool because this allows us not only to see things, but to know how far things are, how large things are, to digitize, if you will, what we observe on the surface of Mars. The rover uses very innovative entry, descent, and landing system to get onto the surface. So we have a heat shield that hit the atmosphere at about 12,000 miles an hour. But even though it's a very thin atmosphere, it slows us down to about Mach 1. And then we deploy a parachute. We float down in the parachute to where we get close to the ground. We fire a set of retro rockets. And then a set of airbags inflate around the rover and its encapsulated lander. And then the bridle is cut and that airbag hits the ground and this $500 million rover bounces around like a giant beach ball on the surface. Eventually comes to rest. The airbags deflate, revealing the rover. And here we are on the surface of Mars. This is January of 2004 when we landed. This is the lander that brought opportunity to the surface. Obviously, the rover is taking the picture here, and you can see where the rover has driven around. And it turns out that this beach ball rolled into this small crater called an Eagle crater, and right at the edge is exposed bedrock. And this was an aha moment. Because here's the rover driving up. You can see the wheel tracks. No, these are not boot tracks, they're wheel tracks. And you can see where the rover used its robotic arm to grind into the surface rocks and make measurements. And if you look carefully, notice these lineations, these horizontal lineations in the rocks. These rocks were formed in an aqueous environment. Rocks don't form in water overnight. They take geologic time to form. So this is conclusive evidence that there was sustained liquid water on the surface of Mars for an extended period of time. Mars must have had a thicker atmosphere over that time and must have had warmer, more Earth-like temperatures during that time. Our rovers were designed for 90 days. Opportunity operated for 13 years. And we far exceeded the capability. The rovers eventually stopped working. We had some failures along the way, and this is one of them. So this is Spirit. The right front wheel on Spirit stopped, and these wheels, they have a large gear reduction motor. When the wheels fail, when the motor fails, you can't spin the wheel. It's kind of like one of those annoying grocery store carts that have a jammed wheel. And so when you try to go down the aisleway, the cart is always trying to turn or yaw. And so we were able to drive with the 5 remaining wheels by dragging that one wheel. So we were driving backwards. And the wheel would scuff up the surface. Well, this turned into the biggest scientific discovery of the mission, because it revealed this light cone material. And when we went back and we looked at that and said, what is that? It turns out it's opaline silica. It's amorphous silicon dioxide. So what? Opaline silica forms in a hot aqueous environment. In other words, a hydrothermal system. This is evidence that there were hydrothermal systems on Mars. Okay, we have liquid water, we have warmer temperatures, we have a thicker atmosphere, we now have a source of energy, hydrothermal energy. Here on the Earth, wherever we find a hydrothermal system, we find a thriving ecosystem. If you go to Yellowstone and you see the geysers of Yellowstone, they're surrounded by these thick stromatolite mats of microbes that are thriving not off of sunlight, but off the hot water coming out of those geysers. You've seen those National Geographic videos of the volcanic vents at the bottom of the ocean. You know, these chimneys of hot water that's like 400 degrees Celsius. And the thriving crustaceans that are living around it, they're getting their energy. They're living off of that thermal energy. Well, here it is on Mars. And so this adds another component to the question: was Mars a habitable world? Well, Spirit and Opportunity are not the only rovers that are visiting Mars. We have 2 other rovers that are there right now. So this is Curiosity. Curiosity landed in 2012. It's a much more capable rover. It's a bigger rover. It carries an analytical chemistry system on board. I think of Spirit and Opportunity as being the geologic rovers for Mars. Curiosity is the analytical chemist for Mars. And you can see some soil samples it took here and it introduced it into the mass spectrometer it has on board, and it found the existence of complex organic compounds. So now we've added another piece to the puzzle. Thicker atmosphere, warmer temperatures, liquid water, hydrothermal systems, and organic compounds. Well, gosh, there's got to be something there, isn't there, on Mars? More recently, we landed Perseverance on Mars. This is during the pandemic. The team at JPL did heroics at completing this mission and launching it and landing it on Mars. Perseverance also carried the Ingenuity helicopter. Even though this is not searching for life, I got to showcase that this is really a tremendous technological triumph to have an aerial vehicle on Mars. Here's the rover landing. We had GoPro cameras, or the equivalent of GoPro cameras, on the landing system. I don't have it here, but I encourage you to go to the web and look up the landing videos from Mars. They're absolutely spectacular. You can see the rover touching down on the surface of Mars with the SkyTrain system. Here is Ingenuity on the surface of Mars, and here is it taking flight. This is our kitty hawk moment. This is historic. This is the first time that humanity has had powered flight on another world, and a tremendous accomplishment. Here's a image taken by Ingenuity looking down at the surface of Mars. You might think, gosh, this kind of looks like Arizona. Can't you imagine, somewhere west of Sonora? It does look very Earth-like. This illustrates the importance of exploring other worlds like Mars with helicopters. The yellow trajectory on here, the yellow line, corresponds to the flight path of Ingenuity. The white corresponds to the trek of Perseverance, the rover. So the helicopter would fly and do reconnaissance of the surface and then guide the rover on the best route. So for example, notice this dune field here, which would be dangerous for the rover to cross, was scouted out by Ingenuity, and then Perseverance was able to traverse successfully around it. So what's Perseverance doing? It looks like Curiosity and has a robotic arm, but notice it is taking core samples of the surface. And it's putting those samples into these cigar-sized sample tubes it is collecting samples that is the first stage of a robotic sample return mission from Mars. What we are working on right now is we have Perseverance on the surface of Mars collecting samples. We are in the process of developing a lander that has a launch vehicle that will fly to Mars, land near Perseverance, deploy a fetch helicopter, retrieve those samples, bring them back to the lander, launch them into orbit, have a orbiting spacecraft rendezvous with those samples, and then return them to Earth to have them thumped down in the Utah Test and Training Range in about 10 years' time. Because only then, when we have samples carefully selected from the surface of Mars, brought back to Earth, and analyzed on the Earth with all the analytical capability we have of all the science labs all over the entire planet, will we be able to definitively answer the question about life on Mars, either past or present. And so now, just in our own solar system, beyond the Earth, we have, Europa, Titan, Enceladus, and Mars, several locations where there could be putative environments that support life. And we go back out to that number I had of, 4 times 10 to the 22 places in our universe? Oh gosh, I think there are a lot of places in our universe that might have life. So, are we alone? We are poised to be really close to answering those questions. Maybe in 10 years we will have samples from Mars to answer the question about life on Mars. But our instrumentation, our capabilities are accelerating every single day. I mean, the James Webb Telescope is just one step towards exploring the universe. We have the Nancy Grace Roman Space Telescope in development right now, which has a coronagraph that is intended to do direct imaging of exoplanets eventually. So we are really making great progress on this question about life in the universe, or life beyond the Earth. But that's not the only scientific question that we are challenged with right now. This is the Triangulum galaxy. It's spectacular, M33. And when we look at this and we start to measure the velocity of the stars in orbit around this galaxy, the center of this galaxy, we find there is a problem. In fact, if I were to plot it here, so here is distance from the center of this galaxy, and then here are the velocity of the stars. What we expected the velocity distribution of the stars to be would follow a curve like this. And this is based on our understanding of gravity, Newton's laws, and how much mass we have determined is in that galaxy. But this is what we observe from two different techniques. And it's like, whoa, did we really blow that one? What happened here? What this tells us is that there is a lot more mass in this galaxy than we see in the stars. Because we just measure the mass of the galaxy by the stars that we observe, we get this. But by doing these gravitational measurements, we get this much mass. So we have this huge disconnect between the two. There is a tremendous amount of unobserved matter in that galaxy. This is the bullet cluster. These are two colliding galaxies. And the colors here correspond to different observational techniques. The red correspond to X-ray observations by our astronomical X-ray telescopes in orbit. And they tell us where the hot gas is for these two galaxies, the stars. And you can see that they're experiencing shock waves as they collide with each other. But if we use the technique of gravitational lensing, which is represented by the blue, we get the mass distribution of these two galaxies. And you notice they're different. The stars are clustered here and here and are deformed by the impact, the collision of these two galaxies. But the predominance of the mass of the two galaxies are here and here, and they are unperturbed because they just pass through each other. And it's like, what's going on? Well, this difference, the previous slide and this one, is suggestive of the existence of dark matter. There is some non-luminous matter that doesn't interact through normal forces as we would expect here, but only interacts gravitationally. And when we look at, going back to this image that I showed you before, and we start measuring the distances and velocities of these galaxies as they recede from us because of the Big Bang, we find that it's different from our model of general relativity. So if you go with general relativity predicts, we either have a closed, flat, or open universe, depending on the constant that comes from the integration of the Friedmann equations. I can go into that for anyone who's interested afterwards. But we had three models for it. Either we had a recollapsing universe. In other words, the universe explodes, goes out, and then comes back again, does what we call a big crunch. Or that it expands along critically, it's going out, and it's slowing down, but it keeps expanding, but at an ever slower rate. Or it's coasting, and then eventually it will come to a stop, but it'll just enough to stop. But what we find is that it's not following any of those trajectories. Here's now in our universe, and so we're looking back in time as we look back at these galaxies, because we're looking at older light, we're looking back in time, and we see that they cluster around this trajectory, which corresponds to an accelerating universe. Why is our universe accelerating? Well, one explanation would be that there is something some source of energy we don't know about. We call it dark energy. Oh gosh, so we got this dark matter. We have this dark energy. When we look back at the birth of our universe, going back to the Big Bang by looking at the cosmic microwave background. So we put a spacecraft in orbit that looks for very cold temperatures. The cosmic microwave background is only about 3 degrees above absolute zero, about 3 Kelvin. And we look at what our universe is, we get this speckled picture of it. Now, this has been highly contrast stretched, but the difference between blue and red is about 10 parts in a million, so 1 part in 100,000. So it's very, very smooth, but there's a structure to it. But by studying this, we can get an idea of how much mass there was at the beginning of the universe. And it's much more than we see today in the luminous mass of our universe. You know, those 10 to the 22 stars, those 100 billion galaxies out there only corresponds to about 4 or 5% of the total mass energy of the universe. About 25% of the universe is dark matter, and the other 69% is dark energy. And we don't know what these things are. Now we have these two great theories about our physical world. The standard model of particle physics, basically quantum mechanics, and general relativity, the theory of gravity. And they've done a magnificent job of explaining our universe. I mean, you know, these devices we carry around in our pockets, we were able to develop these things because we understood quantum mechanics. It works really well. If we didn't have a good understanding of our subatomic world, these devices would not exist. But yet, those theories fail to explain dark matter and dark energy. So this is the Large Hadron Collider at CERN in Europe. It's a giant particle accelerator. And this magnificently confirmed the standard model and detected all the standard model particles, and most recently what's called the Higgs boson. And you know, this is a 27-kilometer tunnel under the ground that accelerates things. They use these giant detectors. That's a person standing there, so you get an idea of the scale of this thing. Well, the Large Hadron Collider has been unable to find any new physics beyond the standard model. Nothing that would explain dark matter or dark energy. This is Super Kamiokande. This is a giant underground detector in Japan that's filled with 50,000 tons of highly purified water. So that's a couple of people in a boat floating inside this giant detector that is surrounded by 11,000 photomultiplier tubes, 11,000 detectors. And they're trying to look for things that happen, trying to find new physics. And they haven't found anything. Zero, nada, that's going on. Here's another. This is Lux Zeppelin. This is another particle detector that's several thousand feet underground in an abandoned iron mine to get away from the noise and radiation of the world, trying to look for new particles. And it hasn't found anything. So it's like, wow, how can we be so successful in making smartphones and explaining, you know, the structure of our universe? Yet we have no explanation for the majority, for 95% of our universe. You know, when I went to school, if you only knew 5% of the subject, that was an F. And so right now, we're getting an F on understanding our universe. You know, so this thing, they put this deep underground, so this is a mine shaft where they have it sitting. So maybe what we need to do is to go back into space. Why would you want to go into space? Well, if you could make an ultra-precise sensor and set it free in the weightless environment of space from the noise and hustle and bustle of the Earth, such that you could listen very quietly to the secrets of the universe, it might reveal something. So what you could do is you could take an atomic clock. Now, atomic clocks use atomic spectra that are very precisely known as the clock mechanism. And so you can make a clock that is accurate to, you know, one part. Let's see, actually, I think I have a clock here. So yeah, it's just a graph of atomic spectra for those that are interested. And then here's the progress we made on the performance of clocks. And this is the error of the clock. So we're now over here with our new strontium optical clocks, better than 1 part in 10 to the 18. So that is a number with 18 zeros behind the decimal point. That's the level of precision that we have with these clocks. Give you an idea of how precise it would be. If we had this clock at the beginning of the universe, at the Big Bang, and it ran all the way till today, it would still be accurate to within half a second after the age of the universe. So what good is a clock? Well, a clock not only tells time, it's also a very precise sensor. Putting a clock into space, you could look to see if that clock tick rate changes. Why would it change? Many of the theories that try to explain dark matter and dark energy say that one of the phenomena would be the presence of new forces or new fields or changes in the fundamental physical constants. And any of those would change the tick rate of the clock. You saw the movie Interstellar, you know, Matthew McConaughey, you know, he flies near a black hole, And because he spends so much time near the black hole, his clock ticks differently from his daughter. So by the time he comes back to Earth, his daughter's a grandmother because her clock was ticking at a faster rate than his clock, because gravity affects time. And so with a clock in space, we can measure gravity to exquisite precision, down to 1 part in 10 to the 18. So we can test gravity to a level of precision that's never been tested before to see if we do have the correct theory of gravity. And maybe some of the answer to the questions about dark matter, dark energy. We can also use the moon as an experiment. We can fire lasers. We have been firing lasers at the moon. We put reflectors on the surface of the moon back in during the Apollo program, and we're still using them today. So 60 years of laser ranging data from the Earth, but we can improve on that. But by precisely measuring the distance the moon is from the Earth, not only do we know when those great lunar and solar eclipses occur, but we can map gravity and the forces of nature again to exquisite precision. Right now, we can measure the distance to the moon from the Earth to about a centimeter. With new technology, we can get that down to 100 microns. And with that kind of precision, the moon becomes a giant test mass. So just like, remember the story of Galileo going to the top of the Tower of Pisa, dropping 2 different sized objects, testing what you call the equivalence principle. We can use the giant mass of the moon as a huge macroscopic version of that, but with exquisite precision. And again, seeing with these precise measurements in space, we may be able to answer some of those fundamental questions. And then ultimately, we can put what are called atom interferometers in space. What's an atom interferometer? Well, quantum mechanics tells us that particles have a wave-particle duality, that electrons can behave like waves, just like photons of light behave like waves. And because they behave like waves, we construct an interferometer, just as you could do with optics. Some of you may be familiar with optical interferometers that you use for laser ranging. They use this very precise instrumentation in the laboratory. We can make an atom interferometer. Okay, why would you want an atom interferometer when you could just use a light interferometer? Well, gravity affects things that are massive. Gravity affects light. But because you're using atoms instead of light, gravity affects, I should say that the atom is many orders of magnitude more massive or equivalent to the mass of a photon by like 9 to 12 orders of magnitude. We're talking 1 billion to 1 trillion times, which means that an atom interferometer that you might construct like this could be 1 trillion times more sensitive than an optical interferometer. Again, a very precise device that we would put into space. And we get several advantages of going into space because what you see here are laser beams that are cooling the atoms down to near absolute zero. So the atoms aren't bouncing around like you would have in a thermal environment here on the Earth. They are actually so cold that they barely move. And we use magnetic fields to control them, but then eventually we turn off the magnetic fields and we just let the atoms sit there. And so they're very quiescent, and so we can then, again, using laser beams to tickle them, make these interferometric devices out of them in the quiescent environment of space and map or test gravity and any other putative forces that might be there, because now you have a device that is 1 trillion times more sensitive than anything that we would have here on the surface of the Earth. So with these instruments that are coming into play today, for example, the first version of this is called the Cold Atom Lab, and it is on the International Space Station right now. In fact, starting on Monday night, the astronauts are going to do an upgrade of this instrument because we've added new capabilities to it. Then we eventually, though, will build new atom interferometers to launch into space. And so this new suite of ultra-precise instrumentation in space, which, by the way, is the program that I mentioned, that I manage for NASA, that's why I'm talking about it, we hope to answer these questions about the fundamental physics. Why is it that our current theories are incapable of explaining these significant phenomena that we are observing out in our world? And the hope is that in addition to answering the question about life in our universe, we'll be able to answer the question about what's dark matter, what's dark energy, and what does it tell us about our understanding of our universe. Thank you very much.
Yes.
I would be pleased to take any of your questions.
Sure.
Thank you for the great talk. A few years ago, I heard something, and I'd love to hear if there's more information, that one of the rovers had detected methane, and that it was seasonally varying. Do you know anything more about that, or could you speak to what you might think that would be?
Yes. The Curiosity, which has the analytical chemistry system on board, has detected methane. That was one of the objectives. And it is seasonally variable, and we still don't know its origin. Okay, the great question is it biogenic or is it abiogenic? Is it produced by natural phenomena or is it produced by a biological system? Just to give you an idea of how much methane we think there is on Mars right now, it's about 2 cows worth distributed over the whole planet, so it's a tiny amount. We've even had ground-based observations of methane, but we still don't know its origin.
Hi. Do you think the dark energy could be equivalent to Einstein's cosmological constant?
Right, great observation, yeah. So there is this free parameter that Einstein put into the general theory of relativity called the cosmological constant, and at the time he thought it was one of the greatest blunders he ever did. Because he was trying to understand at his time, 100 years ago, he thought the universe was static. And so he had to put in a fudge factor to keep the observation of the universe static. But then, decades later, it was found that the universe is actually expanding, and so you didn't need the cosmological constant. But now it's come back in vogue, only with a different value, to explain the acceleration of the universe. So what might that cosmological constant be? And so people have postulated, is it the quantum fluctuation of the vacuum of space? Problem there is that the estimates of what the quantum vacuum fluctuation would be, if it exists, is 120 orders of magnitude different from what we observe. So that's a pretty big fudge factor, even bigger than the number of exoplanets out there. So yeah, we don't know what it is, and that's one of the reasons why we're exploring that question.
I got that for a second.
Incidentally, the gentleman who just asked that question was last month's speaker. This is Dr. Peter Love, or Dr. David, I think, aren't you? Are you our speaker for last? It's Dr. David. Yeah, okay. Well, Dr. Love, everybody give him a hand. His speech was on the James Webb, and it was very well received. And thank you for coming tonight. Anybody else have a question?
Here's the lady over here.
This is going back quite a ways in your talk, but I was fascinated knowing about sort of transit darkenings as a way of getting both an idea of the presence and mass period of a star, but I didn't know about the Doppler shift of the spectrum. What bothers me in that, and I'd just like to understand it, is if the wobble of the star on which this exoplanet is moving tells you something about the mass of the exoplanet, to know how much it wobbles, don't you need to know the mass of the star?
Yes, you do.
How do you find out?
And so we make an estimate of the mass of the star, and there are a number of techniques. One is just by looking at the luminosity of the star, and so we can give an estimate. And we know the size of the star, and then you can see how that star interacts with other celestial objects nearby, by precisely measuring its proper motion. So we can get a pretty good idea of the star's mass. But you're right, there's an uncertainty associated with that, which means there's an uncertainty associated with the mass that we measure for each planet. But right now, we're just trying to get a ballpark estimate of the mass of the planet.
There's been a whole lot of activity trying to figure out what dark matter is. Is there any activity going on to try to figure out what a field is? I mean, we all take this for granted, you know, I mean, it exerts force from a distance, but there's nothing touching. They describe it in mathematics, and they understand the mathematics, but don't know what it is. It seems to be duality with particles. Maybe particles are made out of fields, but nobody seems to know what, if they know what a field is, maybe they know what a particle is.
Yeah, so, we don't know.
They don't seem to worry about not
you know,
knowing.
we have a theory, you know, this theory called, the standard model. It's based on what we call relativistic quantum field theory. And the underlying idea is that everything is a field, that particles are fields. We experience on our level them as being solid material objects, but at the subatomic level, that they behave very differently. So yeah, we don't know if dark matter and or dark energy are a new field or are deviations in our current theories, modifications to gravity, general relativity. There's a whole trade space of possibilities, and everyone has their idea. There is no shortage of theoretical predictions about what it might be. What we need to do are measurements to see if we can test those theories and roll them in or out based on what our measurements tell us. And that's what we're poised to do.
They are thinking about it, they're worried that they
Oh
don't-
yeah. Oh yes, they are, indeed. Any other questions?
It's so hard for me to wrap my head around time as a
I'm sorry,
concept.
maybe a little hard.
It's so hard for me to wrap my head around time as a concept, and then wrap my head around it changing, and then why it would change. So I'm just wondering if you could shed some light on those things.
Yeah, this is these are hard concepts because to investigate these questions, we have to go into a realm in which our normal intuitive experience fails us. When we go into the quantum world, things behave very differently than they do on the everyday level. And the concept of time changing, of our fundamental physical constants changing. I mean, when we went to school, we learned about in chemistry, the mass of the electron, was given as this fixed number. And now people are saying, well, maybe it's not fixed. Maybe it changes. And it's like, well, wait a minute, but they always told me it was fixed. And so we're challenging the notions that we've grown up with in the scientific world. And it's not unlike, 100 years ago when the quantum theory and relativity first came onto the scene, because we had Newton's laws that did a magnificent job of explaining our universe. And we had electromagnetism. And, in the late 1800s, we had this incredible explosion of innovation. The invention of the telegraph, and then the telephone, and then the light bulb, and the Marconi wireless. Those last three all occurred within a couple decades of each other. Once we had this successful theory about electromagnetism, and Newton's laws, they allowed us to find the planet Neptune based on the perturbations to Uranus's orbit. And so these were successful theories that allowed us to do a great explosion of innovation and industrialization of this Earth. But we had these nagging problems at the time that we couldn't understand. We couldn't explain black body spectrum. We couldn't explain atomic spectra. And it wasn't until the quantum theory came along. And we couldn't explain the precession of the perihelion of Mercury. And it was such a tiny effect. People say, well, no, it's only because there's some planet out there we haven't found. But it was explained by the general theory of relativity. And when we developed quantum mechanics and we developed general relativity, we had yet another explosion in innovation. The transistor, the laser, the MRI, these devices are all a result of that level of innovation. So today we have these great scientific questions we don't understand. We can't explain with our current theories, even though those current theories have been very successful. Who knows what kind of innovation might come out of explaining these new phenomena that we're trying to understand. I'd be glad to hang around afterwards with any questions, but I'll thank you again for having me here.
I
there's going to be a presentation here.
You know that we gotta give the guy something because he did good. Let's give him a big round of applause. Our beloved princess manager, Mrs. McPartland, who's in Ireland, is our outreach guy, her husband, left me some gifts for you, even an extra one, because normally we give our priceless porcelain cup that is a big seller here at the museum. It's in here, and I can't seem to get it open. I need a knife or a pair of scissors, so I'm just going to give you this, along with that incredible SBAU tote bag. And then a little something to cover your gas coming up here, sir. No, endorse it, give it to your wife, and then you don't have to report it. They're all right with it. I know what it costs in gasoline to get here. Well, then whatever you decide, no big deal.
Thank you very much.
I appreciate it. Next month, we'll be down at the Fair and Hall, and it'll be Bob Berman on the big screen, Zoom speech, something about 95 and on, the different changes, which is, I guess, the year we launched the Hubble. That was 95, wasn't it? I believe it was. So the Hubble stuff and Webb. And please tell your friends and join the club. We'd like to watch our SBAU podcast, SBAU Astro Hour on Monday morning. Tell your friends, come back. Thank you.